So yesterday's class was our first introduction to double integrals. So we learned how to compute the volume underneath the graph of a function of two variables that lies above a region in the xy plane. When that region is a rectangle, we didn't have to do too much work to determine what limits of integration that we should use, because rectangles can be described with inequalities on x and y that are bounded by constants. So vertical lines, x equals constant, and horizontal lines, y equals a constant. And then we looked at how to use other kinds of regions in the xy plane that might be bounded by functions of x and y. So that led us to what I call the tape measure method, right, which was this way of figuring out how to describe a region using cross sections. So, for example, a type 1 description of a region would bound y in between a pair of functions of x, and then squish that region onto the x-axis and let x be bounded in between two constants. A type 2 description flips that around and allows us to bound x between two functions of y, so that our cross sections look like these horizontal slices, and then squish that onto the y-axis, and then tape measure constant bounds on the y-axis. So today we have two things on the agenda. One of them is to sort of do what we probably should have done in the first place and motivate why we would want to compute a multiple integral, like a double integral, in the first place. Like, what do double integrals actually tell us about quantities that might be of interest in applications outside of mathematics? So in physics and in probability theory and in economics, what are double integrals actually telling us? So that's going to be the first thing that we tackle, looking through a few applications of how double integrals typically get used out in applications. And then after that, we're going to come back to the tape measure method one more time, except instead of tape measuring a region using rectangular coordinates x and y, we want to build the flexibility today to be able to describe regions using polar coordinate descriptions r and theta. So if I had a region that looked like the intersection of the red and blue shades here, if that were my region, Desmos actually isn't able to just shade that region, so we have to consider it to be the intersection here. Then how can I define this region, tape measure this region as being bounded by r equals an inner function of theta and r equals an outer function of theta? And then I have some limits on my theta. Theta goes from 0 to some final value, whatever that final value might be. And then once we've tape measured a region in polar coordinates instead of rectangular, we're actually also going to have to change a little bit how we evaluate that integral. So this is something, again, that we didn't encounter in single variable calculus. In single variable calculus, we didn't really explicitly talk about how to change our coordinate system that we would use to describe the domain of our integral. Secretly, we did. Secretly, it was called U substitution. Doing a U substitution in single variable calculus is really secretly affecting a change of coordinates on the real number line that then has an impact on how we evaluate the integral. When we switch from dx to du, we end up getting this factor of u prime of x that multiplies our integrand along the way. And so a similar thing happens when we change coordinates for two variable integrals, so double integrals, is that we're going to change from dx and dy into, for example, in polar, dr and d theta. But along the way, we have to also multiply by this factor that is going to be the analog in two variable integrals and double integrals of that multiplying by u prime of x that we do when we do a single variable u substitution. The problem, though, is that u prime of x is an ordinary derivative in single variable calculus. Here, the thing we're going to have to multiply has to, in principle, take into account all of the different derivatives of our coordinate change. And so it could have derivatives of r with respect to x, it could have derivatives of r with respect to y, it could have derivatives of theta with respect to x, it could have derivatives of theta with respect to y. All of those could potentially bear upon the thing that we multiply by to affect our change of coordinates from xy into r theta. And so that's going to be the end of our story today, is figure out what do we have to do differently to evaluate an integral in polar coordinates, which very often is a much easier way to understand a region that we're trying to describe. It would be kind of a nightmare to describe this particular region behind me in terms of functions of x and y. But also, it's very often an easier way to understand the function that we're integrating, particularly if our function has some nice radial symmetry, for example. Then it wouldn't depend on theta at all. It would only depend on r, whereas its xy expression would depend on both x and y, and it might have some nasty square roots and stuff that we don't want to have to deal with when it comes time to take antiderivatives. So there are a lot of good reasons that we would want to use polar coordinates to describe our function and to describe our region rather than rectangular. And so that's what we're going to do as our second act in today's class.